How do exponents affect how we combine like terms? Before we answer this question, let's first make sure we understand how to write a numeric expression using exponents, and we're going to use this model to help us with this. Let's take a look at this right here. This represents 12. If you were to count each individual square, you'd get 12 there. If you count how many of these rods, we'll call them, that we have 6 of them. 1, 2, 3, 4, 5, 6. So that would be, as a numeric expression, 6 times 12. We're adding to that, we have 5 of these. Now if we pull this up and look, you can see that that's a 12 by 12 square. So in other words, that's the same thing as 12 squared, or 5 times 12 squared. We're adding to that, we have 3 of these. So what shall we call those using a numerical expression? Well, if each side is 12, if it's going 12 wide, 12 tall, and 12 back, that's 12 cubed. This is a numeric expression that matches the picture that you have. Now, of course, we could simplify that, but we're not going to be worried about that right now because we're just making sure we understand how each of these is different. Something squared is different than something cubed. All right, so now let's apply that to this. Now here we see that we have 4. And we have 4 of those. So 4 of the 4s. We're adding to that 2 of these. So we have 2 of those, and isn't that the same thing as 4 squared? Each of these is 4 squared, or 16. We have 2 of those. We're adding to that, we have in this case 3 cubes, and they're 4 by 4 by 4. So 3 of the 4 to the 3rd power, or 4 cubed. This is a numeric expression that fits this situation. Now let's see if we can understand how this relates to this question of how do exponents affect how we combine like terms. Now down here I have a model that represents 2 different colors. So let's use the variable B for blue, and we'll use the variable R for red. Now let's start out, we don't know what this is, so this could be 4, this could be 5, so let's look at the one that we do know. It could be any value, but we do know we have 1, 2, 3, 4, 5, 6, 7, 8 of those. So if we're going to write an expression that's going to combine everything we see here in this image, we have 1, 2, 3, 4, 8, 1, 2, 3, 4, 5, 6, 7, 8 of the blues. So let's write that down. We have 8 blues. Alright, so if we're talking about things that don't have exponents, let's look at how many of the reds we have. This is a different value. You can see that it's also going to be a greater value than whatever the blue is. So if this is, let's say that this is 4, this might be 7, for example. We have 4 of the reds. 4 of the reds. Plus, now let's look at the squared versions of this. Now if I hold this up, this could be 4, it could be 5, we don't know, but see how the sides match there? This is the squared version of this, so we're going to call this b squared. We have 2 of those. 2 of the b to the 2nd power. 2 of those. Some people like to put that in parentheses, but it's not necessary. Alright, let's take a look at other things that might have an exponent of 2. I have that here in red. Now notice that the length of this is going to be the same as this piece. Well, it's not quite as I meant it to be, so maybe I didn't make the model quite right, but I intended it to be. So there are 3 of those. 3 of the what? 3 of the r squared. Plus 3 of the r squared. And now let's take a look at the things that we're going to call cubic. We have 4 of these. Now if I hold this up, you can see that the dimensions of it match. 4 of those. 4 of the b cubed plus, and then I have just 1 of these, so I'm just going to call that r cubed. I could put a 1 in there, but it's kind of understood that there's 1 there. So what we're looking at here is we're looking at all the like terms combined, and this is as simplified as you can get it. There's a lot going on here on the page, but I'm hoping you understand the difference between the B and the R and why they have to be in, you can't combine the B's and the R's together.